Welcome. Welcome to Sleepy Science Tales. If you're here, it means you're ready for something different. A journey not of action and excitement, but of gentle wonder. Tonight, we're going to explore one of the deepest questions that physics has ever asked. We'll walk through ideas that have occupied the greatest minds of the past century, and we'll do it slowly, thoughtfully, in a way that invites rest rather than tension. I'm so glad you're here. Before we begin, if you find value in these calm explorations of science, I'd deeply appreciate it if you'd take just a moment to like this video. It helps others find their way here, to this quiet corner of curiosity. And if you haven't already, please subscribe to Sleepy Science Tales and share this with anyone who loves to drift off while contemplating the mysteries of existence. Your support means the world, and it allows us to keep creating these journeys together. Now, let your shoulders drop. Relax your jaw. Let your breathing settle into its own natural rhythm. You don't need to do anything but listen. You don't need to remember every detail. Just let the ideas wash over you like gentle waves. Tonight, we're asking a question that might sound strange at first. When does space-time become quantum? It's a question about the very fabric of reality, about whether space and time, those things that seem so solid, so reliable, might actually be very different when examined closely enough. It's a question about where our everyday experience meets the deepest laws of nature. And it's a question that reveals as much about the limits of human understanding as it does about the universe itself. We'll travel from the familiar world of everyday experience, through Einstein's elegant geometries, into the probabilistic strangeness of quantum mechanics, and finally to the frontiers where physics itself becomes uncertain. We'll meet ideas with beautiful names: quantum foam, spin networks, holographic principles. We'll encounter the Planck length, the smallest meaningful distance in nature, and we'll discover that sometimes the most honest answer science can give is not a fact, but a boundary. There's no rush. We have all the time we need. Let yourself settle in. Let your mind wander when it wants to. These ideas will be here, patient and steady, waiting for you. Let's begin softly, with the world as we know it. Close your eyes for a moment, if you'd like. Imagine the room around you. Feel the surface beneath you. Notice how solid everything seems, how that everything is. Space extends outward in every direction, from where you are to the walls, from the walls to the street outside, from the street to the horizon, to the sky, to the stars. Distance feels real, doesn't it? Measurable, stable, predictable. And time flows. One moment follows another in perfect order. The past is behind you. The future is ahead. The present is this breath, this heartbeat, this quiet instant of awareness. This is how reality presents itself. Continuous, unbroken, smooth. A path from here to there doesn't skip over any distance. It connects every point along the way. A minute doesn't jump from second to second with gaps between. It flows seamlessly, like water, like music, like breath, for most of human history. This is how we understood the world. Space was an empty container in which things could exist. Time was a river that carried events along. Both were infinitely divisible. You could always imagine a smaller distance, a briefer moment. There was no end to how finely reality could be sliced. This intuition shaped mathematics. A line could be divided endlessly. Between any two points, another point could always be placed. Geometry assumed continuity not because it was proven, but because it seemed obvious. It matched experience so perfectly that questioning it felt unnecessary. When physics began to formalize the laws of motion, it adopted these same assumptions. Isaac Newton, in the late 1600s, described a universe of absolute space and absolute time. Space existed independently of anything within it. Time flowed uniformly, identically, everywhere. Objects moved through space. Events unfolded in time, but neither space nor time were affected by what happened within them. This framework was extraordinarily powerful. It could predict the motion of cannonballs, the swing of pendulums, the orbit of the moon. It worked so reliably that it became the foundation of engineering, navigation, and astronomy. Bridges were built using these equations. Ships sailed by calculations based on them. Centuries of technological progress rested on the assumption that space and time were smooth, continuous and absolute, and for almost all practical purposes, they still are. When you drive to work, space doesn't suddenly become granular. When you watch a clock, time doesn't stutter or skip. The continuity we experience is genuine. It's not a trick or an illusion. It's an accurate description of how reality behaves at the scales we inhabit. But here's the thing: accuracy at one scale doesn't guarantee accuracy at every. Scalea beach looks smooth from a distance. Walk closer and you see sand. Look closer still and you see grains with gaps between them. Closer yet, and those grains dissolve into atoms, into particles, into something that no longer resembles a solid surface at all. Nothing about the beach changed. Only the scale of observation changed. Could space and time be the same way? Could their apparent smoothness be a feature of how we observe them, rather than what they truly are? For centuries, no one had reason to ask. The smooth, continuous framework worked perfectly. There were no experimental results that contradicted it, no mathematical inconsistencies that demanded revision. But as measurements grew more precise, as technology allowed scientists to probe smaller distances and briefer moments, something subtle began to emerge. At very small scales, the rules changed. Matter stopped behaving classically. Energy came in discrete chunks. Certainty gave way to probability. And a comfortable, continuous universe began to look less like a fundamental truth and more like an approximation, a very good approximation, but an approximation nonetheless. This realization didn't happen all at once. It crept in slowly, through decades of careful experiments and theoretical breakthroughs, and it raised a quiet but profound question: if matter and energy behave quantum mechanically, at small scales, what about space and time themselves? Do they remain smooth no matter how closely we look? Or is there a point, some threshold, some boundary where space and time stop being the familiar, continuous things we know, and become something else entirely? That's the question we're here to explore. Not where this happens, because it's not about location, but when. At what scale? At what resolution? At what point does the description we trust begin to fail? Let's find out together, gently. To understand where we're going, we need to appreciate where we've been. And for a long time, centuries, really physics lived in a world of beautiful, reliable smoothness. Imagine a universe where everything makes sense, where every effect has a cause, where motion follows precise mathematical laws, where if you know the position and velocity of every object, you can predict the future with perfect accuracy. This was the universe of classical mechanics, and it worked spectacularly well. Isaac Newton gave us this gift in 1687 with his Principia Mathematica. In it, he laid out 3 laws of motion and a law of universal gravitation. Together, these simple principles could explain almost everything that moved. An apple falls because Earth's gravity pulls it downward. The moon orbits Earth because gravity provides exactly the right force to keep it in circular motion. Planets trace ellipses around the sun because gravity weakens with distance, according to a precise mathematical rule. What made this framework so powerful wasn't just that it explained things. It's that it explained them quantitatively. You could calculate exactly how fast the apple would fall, exactly how long it would take, exactly where it would land, and those calculations were never wrong. Well, almost never. There were tiny discrepancies, small anomalies in planetary motion, slight disagreements between theory and observation, but these were so minor that they were easily dismissed as measurement errors, or effects too subtle to matter. Underneath Newton's laws was a simple assumption: space and time are continuous. An object doesn't teleport from one location to another. It travels through every point in between. Time doesn't skip forward in jumps. It advances smoothly, moment by moment. These assumptions weren't controversial. They were invisible. They were so deeply embedded in how people thought about reality that they weren't even recognized as assumptions. They were just the way things were mathematically. This meant that physics was built on calculus, the mathematics of continuous change. Velocity is the rate at which position changes with time. Acceleration is the rate at which velocity changes. Forces produce accelerations. Everything flows smoothly from everything else. And the predictions? Exquisite. Astronomers could predict eclipses centuries in advance. Engineers could design machines with moving parts that meshed perfectly. Navigators could determine their position at sea by observing the stars. And consulting tables based on Newtonian calculations. Classical mechanics wasn't just accurate. It was useful. It shaped the Industrial Revolution. It enabled the modern world. Even today, we use it constantly. When NASA sends a spacecraft to Mars, the trajectory calculations are based on classical mechanics. When civil engineers design a bridge, they use classical equations to calculate stresses and forces. When you throw a ball, it follows a parabola just as Newton's laws predict. At human scales, classical mechanics is indistinguishable from truth. But let's go further. Let's leave Earth and look at the cosmos. The distances involved are staggering. Earth orbits the Sun at an average distance of about 150 million kilometers. The nearest star beyond the Sun, Proxima Centauri, is more than 40 trillion kilometers away. Light, traveling at 300,000 kilometers per second, takes over for years to cross that distance. And yet, Newton's laws work there too. Binary stars orbit each other in perfect gravitational dances. Galaxies rotate according to predictable patterns. Well, mostly dark matter complicates things. But that's another story. The expansion of the universe itself can be traced backward, using equations rooted in continuous space and time. Nowhere in this vast range from millimeters to megaparsecs does classical space-time show cracks. Nowhere does distance become discontinuous. Nowhere does time stutter. This consistency is remarkable. It's not an accident. It reflects the fact that at large scales, the assumptions of classical physics align beautifully with how nature actually behaves. Even time, that most mysterious of dimensions, behaves predictably. Modern atomic clocks measure time using the oscillations of cesium atoms. They are so precise that they lose less than 1 second every 100 million years. These clocks rely on quantum processes within atoms. Yes, but the time they measure behaves classically. It flows. It doesn't jump. And when Einstein revolutionized our understanding of gravity in 1915, he didn't abandon continuity. He transformed it. In Einstein's general relativity, which we'll explore more deeply in a moment, space and time merge into a single entity called spacetime, and spacetime curves. Mass and energy bend it. Objects follow the curves, and we perceive that motion as gravity. But crucially, spacetime remains smooth. It can stretch, compress, ripple, and twist, but it does so continuously. There are no gaps, no jumps, no breaks. At every scale where general relativity has been tested, from GPS satellites in Earth orbit to gravitational waves from colliding black holes, spacetime behaves as a smooth, continuous manifold. So why, then, are we questioning this? Because there's one place where the assumptions begin to fail. One regime where smooth, continuous spacetime stops being sufficient. That regime is not defined by location. It's defined by scale. And by energy. When we try to describe the universe at the smallest distances for tinier than atoms, smaller than protons, approaching the fundamental limits of measurability, strange things start happening. The tools that worked so well begin to produce nonsense. Infinities appear where finite numbers should be. Predictions become meaningless. The mathematics itself protests. Classical spacetime, for all its elegance and success, reaches a boundary. And at that boundary, we need something else. But before we can understand what that something else might be, we need to understand why general relativity works so beautifully. We need to see what Einstein saw. We need to feel how spacetime became not just a stage, but an actor. Let's go there now, softly, into the curved universe. Imagine you're standing on a trampoline, firm, taut, flat. Now imagine placing a heavy bowling ball in the center. What happens? The surface curves downward. It deforms. If you now roll a marble across the trampoline, it won't travel in a straight line anymore. It will curve toward the bowling ball, not because the ball is pulling it with an invisible force, but because the surface itself is curved. This is the essence of Einstein's general relativity. Gravity, in this picture, is not a force that reaches across empty space and pulls objects together. Gravity is the curvature of space-time caused by mass and energy. Objects don't fall because they're being pulled. They fall because they're following the straightest possible path through curved space-time. It's a radically different way of thinking, and it's one of the most beautiful ideas in all of physics. Einstein published his theory of general relativity in 1915, after years of intense work. He was trying to reconcile to things that didn't seem to fit together. His earlier theory of special relativity, which said that the speed of light is constant for all observers, and Newton's law of gravity, which assumed that gravitational effects travel instantaneously, something had to give. What gave was the idea of space and time as separate, unchanging backgrounds. In special relativity, Einstein had already shown that space and time are interwoven. What one observer measures as a distance in space, another moving at a different speed might measure as a mixture of space and time. Lengths contract, time dilates. Space and time are relative, not absolute. But special relativity still assumed a flat space-time. A space-time without gravity. General relativity was Einstein's attempt to add gravity back in, and his insight was astonishing. Gravity is not something that happens in space-time. Gravity is spacetime. Mass and energy tell space-time how to curve. Curved space-time tells mass and energy how to move. It's a feedback loop, a conversation between matter and geometry. Let's take this slowly, because it's worth savoring. In Newton's universe, space is a fixed grid. Objects move through it. Gravity is a force that acts between objects, pulling them together according to their masses and distances. Space itself doesn't participate. It's just the arena where things happen. In Einstein's universe, there is no fixed grid. Space-time is flexible. When you place a massive object, say, the sun, it warps the space-time around it. Nearby objects like Earth respond to that curvature. They move along the curved paths which we perceive as orbits. The sun isn't pulling Earth toward it. Earth is simply following the geometry. And this isn't just a different way of describing the same thing. It makes different predictions. One of the first tests came in 1919 during a solar eclipse. Arthur Eddington led an expedition to observe stars near the sun's edge. According to Newton, starlight passing close to the sun should bend slightly due to the sun's gravity. But Einstein's theory predicted a bend twice as large, because light follows the curvature of space-time, and space-time near the sun is significantly curved. The measurements matched Einstein's prediction. It was a triumph. Newspapers around the world announced that Newton had been overthrown. Einstein became a celebrity overnight. Since then, general relativity has been tested again and again. Every test has confirmed it. Light bends around massive objects, a phenomenon called gravitational lensing. Astronomers now use this regularly. The gravity of a galaxy can act like a lens, bending and magnifying the light from more distant galaxies behind it. Time slows down in gravitational fields, a phenomenon called time dilation. A clock on Earth's surface runs slightly slower than a clock high above the planet. GPS satellites must account for this effect, or their positioning calculations would accumulate errors of several kilometers per day. Space-time itself can carry waves, gravitational waves that ripple outward from violent cosmic events. In 2015, the LIGO detectors captured the gravitational wave signal from two black holes spiraling into each other and merging. The signal matched Einstein's predictions with stunning precision. General relativity is not just a theory. It's a confirmed description of how the universe works at large scales. And crucially, throughout all of this, space-time remains smooth. Curved, yes. Dynamic, yes. But continuous. There's no smallest unit of distance in Einstein's equations. Space-time can be divided infinitely. The mathematics assumes that you can zoom in arbitrarily close and still find well-defined geometric properties. This smoothness is essential to how the theory works. Curvature is defined locally, meaning at every point you can calculate how much space-time is bending. Geodesics, the paths that objects follow, are smooth curves, even in extreme situations. Smoothness holds near a neutron star, where gravity is billions of times stronger than on Earth. Spacetime is wildly curved, but it's still continuous. Near a black hole, where gravity becomes so intense that not even light can escape. Spacetime is even more distorted, but still, mathematically, it's smooth. Until you reach the center, this is where the first hint of trouble appears. At the very center of a black hole, Einstein's equations predict a singularity, a point where curvature becomes infinite. Density becomes infinite. The mathematical description breaks down. Physically, this doesn't make sense. Infinity is not a number you can measure. It's a signal that the theory has been pushed beyond where it applies. Similarly, if you use general relativity to describe the early universe and run time backward, the equations predict that everything was once compressed into a single point. A singularity at the beginning of time. Again, infinity. Again, a breakdown. Einstein himself was uncomfortable with singularities. He suspected they indicated a limit to his theory. But within the regime where general relativity has been tested everywhere, except these singular points, it works flawlessly. So we're left with a beautiful, elegant, extraordinarily successful theory that treats spacetime as smooth and continuous, but hints in its darkest corners that something deeper is needed. And that something becomes unavoidable when we bring in the other great pillar of 20th century physics. Quantum mechanics. Let's go there now, gently, into the probabilistic realm. Take a deep breath now. Imagine trying to describe that breath using only probabilities. Not the exact position of every air molecule, that would be impossible, but the likelihood of finding a molecule in a particular region. The probability that it has a certain energy. This is the world of quantum mechanics, and it's not a limitation of our knowledge. It's the nature of reality at small scales. Quantum mechanics emerged in the early 1900s, not because anyone wanted a strange new theory, but because experiments were producing results that classical physics simply could not explain. It started with light. When physicists studied how hot objects emit radiation, they expected the energy to be distributed smoothly across all frequencies. But that's not what happened. Instead, the energy seemed to come in discrete packets, little bundles, as if light were made of particles, not waves. In 1900, Max Planck proposed a radical idea. Maybe energy isn't continuous. Maybe it can only be exchanged in specific amounts, quanta that depend on frequency. It was a desperate fix. Planck himself didn't fully believe it. But it worked. The calculations matched the experiments perfectly. A few years later, Albert Einstein took Planck's idea seriously. He used it to explain the photoelectric effect, the way certain metals emit electrons when light shines on them. Classical wave theory couldn't explain it. But if light came in discrete packets, photons, it made perfect sense. Then Niels Bohr applied quantization to atoms. He proposed that electrons couldn't orbit the nucleus at just any distance. They had to occupy specific energy levels. They could jump between levels, emitting or absorbing light in the process, but they couldn't exist in between. Suddenly, discreteness was everywhere. Energy levels, photon packets, quantum jumps, and it wasn't just a mathematical trick. It was real. Atoms really do emit light at specific wavelengths. Electrons really do occupy discrete states. But it got stranger. In the mid-1920s, Werner Heisenberg discovered something unsettling. Certain pairs of physical quantities cannot both be known precisely at the same time. Position and momentum, for example. The more accurately you measure where a particle is, the less accurately you can know how fast it's moving, and vice versa. This isn't a limitation of measurement technology. It's fundamental. Nature herself doesn't assign exact values to both quantities simultaneously. Think about that for a moment. In the classical world, every object has a definite position and a definite velocity at every moment. You might not know those values, but they exist. In the quantum world, they don't exist, not in the same definite way. Instead, particles are described by wave functions, mathematical objects that encode probabilities. Where is the electron? The wave function tells you the probability of finding it in various places. What's its momentum? The wave function tells you the probabilities for different momentum values. But until you measure it, the electron doesn't have a single, definite position. It exists in a kind of fuzzy, probabilistic state. This is deeply counterintuitive. It feels wrong. Einstein himself never fully accepted it. He famously said, "God does not play dice with the universe," but experiment after experiment confirmed it. Quantum mechanics wasn't just strange, it was correct, and it was wildly successful. Quantum mechanics explains the structure of atoms. It explains why matter is stable, why atoms don't collapse. It explains chemical bonding, the behavior of semiconductors, the operation of lasers, the principles behind MRI machines, modern technology computers, smartphones. Medical imaging depends on quantum mechanics. It's not optional. It's not speculative. It's the best description we have of how nature behaves at small scales. But here's the key point. Quantum mechanics is fundamentally incompatible with the smooth, continuous worldview of classical physics. In classical mechanics, you can track a particle's trajectory. You can draw a line showing where it was at every moment. In quantum mechanics, you can't. Between measurements, the particle doesn't have a definite trajectory. It's described by probabilities that spread out over space. In classical mechanics, energy varies smoothly. In quantum mechanics, energy comes in discrete levels. In classical mechanics, knowing the present state lets you predict the future with certainty. In quantum mechanics, you can only predict probabilities. The two frameworks rest on fundamentally different assumptions about what physical quantities are and how they behave, and here's where the tension arises. General relativity describes space-time as smooth and continuous. Quantum mechanics describes matter and energy as discrete and probabilistic. Both theories are confirmed by vast amounts of experimental evidence. Both work extraordinarily well in their respective domains, but they don't fit together. In quantum mechanics, space and time are treated as a fixed background. Particles move through space. Their properties change over time, but space and time themselves aren't affected. In general relativity, space-time is dynamic. It curves in response to energy. It's not a background, it's a participant. So what happens when you try to combine them? What happens when you have a situation where both quantum effects and gravitational effects are important? This is where things get difficult. In most situations, you don't need to worry about this. If gravity is weak, you can ignore space-time curvature and just use quantum mechanics. If quantum effects are negligible, like with planets and stars, you can ignore them and just use general relativity. But there are regimes where both matter. Near the singularity inside a black hole, at the very beginning of the universe, at distances so small that both quantum uncertainty and gravitational curvature become unavoidable. In these regimes, neither theory is sufficient on its own. Quantum mechanics assumes a stable space-time. General relativity treats space-time as dynamic. When both effects are strong, the assumptions of each theory undermine the other. Attempts to apply standard quantum techniques to gravity run into problems. The calculations produce infinities that can't be controlled. The mathematics breaks down. This isn't just a technical issue. It's a signal that something fundamental is missing. And it raises the question we've been circling around. If matter and energy behave quantum mechanically, what about space-time itself? Does space-time remain smooth and continuous no matter how closely we look? Or does it, too, become quantum? And if it does, what does that even mean? Let's explore that now, carefully, without rushing. Imagine two friends who speak different languages. Each is eloquent, articulate, brilliant in their own tongue. But when they try to talk to each other, nothing quite translates. This is where physics found itself in the mid-20th century and where, in many ways, it still finds itself today. On one side, general relativity, the theory of space-time and gravity. On the other, quantum mechanics, the theory of particles and fields. Each is spectacularly successful. Each has been tested countless times and never found wanting. And yet, they cannot be reconciled. Not easily, anyway. Let's understand why. The core issue is what each theory assumes about space and time. Quantum mechanics needs a fixed stage. It describes how particles and fields evolve within space-time. The probabilities change with time. Wave functions spread through space, but the underlying framework spacetime itself is assumed to be stable and given. This is called background dependence. The theory depends on a pre-existing spacetime background. General relativity denies that such a background exists. In Einstein's theory, spacetime is not a stage. It's part of the performance. It bends and flexes in response to mass and energy. There is no fixed geometry. The shape of spacetime is what the equations solve for. This is called background independence. These two principles, background dependence and background independence, are fundamentally at odds. Quantum mechanics says, "Give me a spacetime and I'll tell you how fields behave." General relativity says, "There is no spacetime to give you." Spacetime itself must be determined by the dynamics. If you try to apply quantum mechanics to gravity, you immediately run into trouble. In quantum field theory, the framework used to describe electromagnetism and the nuclear forces, you quantize fields. You treat them as collections of oscillators, each capable of holding discrete amounts of energy. Particles emerge as excitations of these fields. This approach works beautifully for forces like electromagnetism. The infinities that appear in calculations can be systematically absorbed into a finite number of parameters, a process called renormalization. The theory remains predictive. When you try to do the same thing with gravity, renormalization fails. New infinities keep appearing at every level of precision. There's no finite set of parameters that can absorb them all. The theory loses predictive power. It becomes, in a technical sense, uncontrollable. This problem was recognized decades ago. Richard Feynman, who pioneered quantum electrodynamics, examined whether similar techniques could work for gravity. His conclusion was sobering. Yes, you can define a quantum version of gravity at low energies, but at high energies, the theory becomes unmanageable. Why does this happen? The key issue is how gravity couples to energy. In general relativity, all forms of energy contribute to spacetime curvature. This includes not just the energy of matter, but also the energy of quantum fluctuations themselves. And in quantum mechanics, fluctuations are unavoidable. Even in a vacuum region with no particles, quantum fields fluctuate. These fluctuations carry energy. That energy, according to general relativity, should curve spacetime. But if spacetime curves, that affects the quantum fields, which changes the fluctuations, which changes the curvature, which, you see the problem. It's a feedback loop, and it's unstable. The more precisely you try to describe spacetime at small distances, the more energy you need to probe those distances. That energy distorts spacetime. The distortion makes it harder to define distance. The whole structure becomes self-undermining. Mathematically, this shows up as infinities. Quantities that should correspond to measurable physical effects diverge to infinite values. This is very different from what happens in other quantum theories. In quantum electrodynamics, infinities appear, but they can be tamed. A finite number of adjustments makes the theory work perfectly. Quantum gravity doesn't cooperate. There's also a conceptual problem. Quantum mechanics relies on the notion of time. Wave functions evolve in time. Probabilities change with time. Measurements happen at specific moments in time. But in general relativity, time is not absolute. There's no universal clock. Time is part of spacetime, and spacetime is dynamic. If spacetime itself becomes quantum subject to uncertainty and fluctuation, then what does it mean for something to happen at a particular time? The very framework of quantum mechanics begins to unravel. This creates a circularity. Quantum mechanics needs a stable spacetime to function. General relativity predicts that spacetime responds dynamically to energy, including quantum energy. Each theory undermines the assumptions of the other. Now, let's be clear about what this does not mean. It does not mean there's an experimental contradiction between quantum mechanics and general relativity. In regimes where both have been tested, they work fine. The problem only appears when you try to apply both theories in situations where both effects are strong at the same time, and those situations are rare. They occur near black hole singularities, at the earliest moments of cosmic expansion, at distances far smaller than anything we can currently observe. In these extreme regimes, Neither theory can be safely applied without modification. General relativity predicts infinite curvature, a sign that its assumptions are breaking down. Quantum mechanics predicts fluctuations that cannot be ignored, a sign that treating spacetime as a fixed background is no longer valid. So, we're left with a clear signal. Neither quantum mechanics nor general relativity is complete. Both are correct within their domains, but neither extends indefinitely. Each points toward the existence of something deeper, a framework that includes both the special cases. Finding that framework is the problem of quantum gravity, and it's one of the hardest problems in theoretical physics, because it's not just about making calculations work. It's about reconciling to fundamentally different ways of understanding reality. One treats spacetime as a smooth, deterministic geometry. The other treats physical quantities as probabilistic and uncertain. When spacetime itself is included among those quantities, the clash becomes unavoidable. But here's the thing, this incompatibility is not a failure. It's a clue. It tells us that the question of quantum spacetime is not academic. It's essential. It tells us that smooth spacetime, for all its success, cannot be the final word, and it tells us where to look, at the place where quantum uncertainty and gravitational effects are both unavoidable. That place is not defined by location, it's defined by scale. Let's go there now, gently, into the realm of scale. Here's a comforting thought. You don't need to know everything about a system to describe it accurately. You don't need to know the position of every air molecule to predict the weather. You don't need to know the quantum state of every atom in your body to understand biology. You don't need to track individual photons to see a rainbow. This is because physics works at different scales, and at each scale, different descriptions apply. This idea that reality is layered, that different frameworks are appropriate at different resolutions, is one of the most important insights in modern physics, and it's the key to understanding when spacetime becomes quantum. Let's start with a familiar example. The coastline. From an airplane, a coastline looks smooth, a gentle curve separating land from sea. You could draw it on a map with a single, flowing line. Zoom in, fly lower, and you see detail. Inlets and peninsulas, rocky outcrops, small bays. Closer still, walk along the beach and smoothness disappears entirely. Jagged rocks, irregular sand patterns, individual pebbles. Zoom in further, examine a single grain of sand under a microscope, and even the grain has structure. It's not a smooth sphere, it's an irregular chunk of mineral. Go deeper still, look at the atoms, and solid matter dissolves into mostly empty space, with tiny nuclei surrounded by electron clouds. At what scale is the coastline really smooth? At what scale is it really jagged? The answer is both. And neither. The coastline doesn't have a single, true nature that exists independently of scale. Its description depends on how closely you look. At large scales, smoothness is an accurate and useful description. At small scales, it's not. The same is true throughout physics. Consider temperature. When you measure the temperature of water, you're measuring the average kinetic energy of trillions upon trillions of water molecules. At the macroscopic scale, the scale of cups and bathtubs, temperature is a smooth, continuous quantity. It rises and falls gradually. It has a well-defined value at every point. But zoom in, follow individual molecules. At that scale, temperature becomes meaningless. A single molecule doesn't have a temperature. Temperature is a collective property that only makes sense when many particles are involved. Temperature is real. It's measurable. It affects processes in predictable ways, but it's not fundamental. It's emergent. It arises from microscopic behavior without being present at the microscopic level. The same is true of pressure, of viscosity, of elasticity. All of these are real, useful, accurate descriptions. At the appropriate scale, this is the idea of effective theories. An effective theory describes phenomena at a particular scale, without needing to capture every underlying detail. It works because those details don't matter. They average out, they cancel. They become irrelevant to the behavior being studied. Classical mechanics is an effective theory. It ignores quantum uncertainty and the discrete nature of matter. Yet it accurately predicts the motion of cars, planets, and projectiles because at those scales, Quantum effects are negligible. Fluid dynamics is an effective theory. It treats liquids as continuous substances, ignoring the fact that they're made of molecules. It works because molecular details average out at larger scales. And here's the crucial point: smooth spacetime might be an effective theory too, at the scales accessible to observation human scales, astronomical scales, even atomic scales. Spacetime behaves as a continuous geometric structure. Curvature changes gradually. Distances and durations can be measured precisely. General relativity works because it accurately captures the dominant behavior at those scales. But this doesn't mean spacetime is fundamentally smooth. It means smoothness is the right description where we've tested it. If spacetime has a more fundamental structure at extremely small distances, that structure wouldn't necessarily affect everyday physics, just as the atomic structure of matter doesn't affect the trajectory of a baseball. The microscopic structure of spacetime wouldn't affect planetary orbits or gravitational waves. This is why experiments haven't detected anything strange. It's not that spacetime is perfectly smooth at all scales. It's that any underlying structure is hidden well below the resolution of our measurements. So, when does the smooth description break down? The answer lies in a concept called the Planck scale. This is the scale where quantum effects and gravitational effects become equally important. It's not chosen arbitrarily. It emerges naturally from combining the fundamental constants of nature, the speed of light, the gravitational constant, and Planck's constant. The Planck length is about 1.6 times 10 meters. To put that in perspective, an atom is about 1 billion times larger than a proton. A proton is about 10 times larger than the Planck length. The Planck length is unimaginably small. And that's the scale where smooth spacetime is expected to fail. Why? Because at that scale, trying to probe smaller distances would require concentrating so much energy into such a small region that spacetime itself would respond violently. Quantum fluctuations would become strong. Geometry would become unstable. Below the Planck scale, the very concept of distance loses operational meaning. You can't measure it without destroying the structure you're trying to measure. This is not a technological limitation. It's a fundamental feature of physics. So here's the picture that emerges. Above the Planck scale, everything we've ever measured spacetime is smooth. It behaves classically. General relativity applies. Below the Planck scale, far beyond current observation, spacetime may be very different. It might be discrete. It might fluctuate wildly. It might not resemble space and time as we know them at all. And crucially, this transition is not about location. It's about resolution. The same patch of spacetime can be smooth when viewed from far away and non-smooth when examined closely. Just like the coastline, this perspective reframes the original question. Instead of asking, when does spacetime become quantum? As if there's a boundary in the universe where things change, we ask, at what scale do the concepts of distance, duration, and smooth geometry stop being adequate descriptions? That question has a clearer answer, the Planck scale. And recognizing this helps us avoid confusion. Quantum spacetime is not hiding somewhere in the universe, waiting to be found. It's a matter of looking closely enough, if we could, at the fabric of reality itself. Let's explore that fabric now, gently, with care. Let me tell you about the smallest meaningful distance in the universe. Not the smallest distance we've measured that's limited by our technology, but the smallest distance that has physical meaning. A distance beyond which the very concept of how far apart begins to dissolve. This distance has a name, the Planck length. And it emerged not from any experiment, but from a simple, elegant question that Max Planck asked himself in 1899. What if we combined nature's most fundamental constants, the speed of light, the gravitational constant, and the quantum of action, into a single length scale? What he discovered was remarkable. When you take these three constants that govern light, gravity, and quantum behavior and combine them mathematically, you get a length, a specific, natural length that doesn't depend on human conventions like meters or inches. It arises purely from the laws of physics themselves. That length is approximately 1.616 times 10 to the power of -35 meters. Let's try to grasp how small this is. If you could magnify an atom to the size of the observable universe, the Planck length would still be smaller than an atom dot. There are as many Planck lengths in a single proton as there are protons lined up across the entire observable universe. Roughly 10 to the power of 40 dot it is. In a very real sense, beyond visualization, our minds evolved to navigate a world of meters and kilometers, of seconds and hours. The Planck scale exists so far outside that realm that any attempt to picture it is bound to fail. But here's what makes the Planck length profound. It's not just small. It's the scale where quantum mechanics and gravity meet is equals. Think about it this way. At large scales, planets, stars, galaxies, gravity dominates. Objects follow curved paths through space-time. The tiny quantum jitter of particles is completely insignificant. At small scales, atoms, electrons, photons, quantum mechanics dominates. Particles exist in probabilistic states. Uncertainty reigns. But gravity? It's negligible. The gravitational attraction between two electrons is about 10 to the power of 43 times weaker than their electromagnetic repulsion. But there's a scale where both effects matter, where quantum uncertainty is strong and gravitational effects are strong, where neither can be ignored. That scale is the Planck scale. And at this scale, something remarkable happens. Measurement itself breaks down. Here's why. To measure a very small distance, you need a probe with a very short wavelength. In quantum mechanics, wavelength is inversely related to energy. Shorter wavelength means higher energy. So probing smaller distances requires higher energies. Now, according to general relativity, energy curve space-time, the more energy you concentrate in a region, the more you distort the geometry. So what happens when you try to measure distances near the Planck length? You need to concentrate so much energy into such a small region that you create a black hole. The energy required to probe Planck scale distances is exactly the energy that would cause space-time itself to collapse into a singularity. At that point, the very notion of measuring a distance becomes undefined. The tool you're using to measure whether it's a particle, a wave, or anything else disrupts the geometry so severely that distance loses meaning. This isn't a limitation of technology. It's not that we need better microscopes. It's that the concept of distance, as we understand it, ceases to function. The Planck length marks a boundary. Not a boundary in space. There's no location where things suddenly change, but a boundary of description. Beyond this scale, the classical notion of smooth, continuous distance simply doesn't apply. The same is true for time. The Planck time is the time it takes light to travel one Planck length. It's about 5.4 times 10 to the power of -40 for seconds. This is the shortest duration that has operational meaning. Below this, the concept of a moment in time becomes as unstable as the concept of distance. Trying to resolve briefer intervals would require energies. That would make the geometry of space-time itself uncertain. Now, let's be careful about what this doesn't mean. The Planck length is not necessarily the smallest chunk of space. It doesn't mean space-time is made of tiny Planck-sized pixels, like a cosmic computer screen. What it does mean is that below this scale, our usual ways of talking about space and time in terms of distances, durations, and geometry stop being meaningful. It's a limit to classical description, not necessarily a literal discreteness. Some theories propose that space and time really are discrete at the Planck scale. Others suggest that space-time remains continuous but becomes subject to wild quantum fluctuations. Still others propose that space-time itself is not fundamental, that it emerges from something deeper, and that emergence only makes sense above the Planck scale. We don't know which picture is correct. What we do know is that the Planck scale represents the point where quantum mechanics and general relativity must be reconciled. Above this scale, space-time can be treated as smooth. Below it, something different is needed. This is not speculation. It follows directly from combining principles that have been tested countless times: quantum uncertainty, gravitational interaction, and the finite speed of light. The Planck scale is a natural consequence of the laws we already know, and it provides a precise answer to the question we've been asking. When does space-time become quantum? Not at any particular location, not at any moment in cosmic history, but at a scale, the Planck scale, where the classical framework can no longer be applied. Without internal contradiction, this is where smooth spacetime reaches its limit. What lies beyond that limit? What replaces the familiar concepts of distance and duration? That's where our certainty ends and our theories diverge. But before we explore those theories, let's pause for a moment in this liminal space, this threshold, this boundary where the familiar gives way to the unknown, because there's something beautiful about recognizing limits, not as failures but as invitations, as markers that say, here be new physics, here be deeper truths, let's rest here, just for a breath. Before we venture further, imagine you're standing at the edge of the ocean on a calm day. The surface looks smooth and gentle, glassy expanse stretching to the horizon. But get closer. Look carefully. The surface isn't perfectly smooth at all. There are ripples, tiny waves, fluctuations driven by wind, by thermal motion, by the complex dynamics of water. Zoom in further, imagine you could see at the molecular scale and the calm surface becomes a frenzy. Molecules jittering, colliding, evaporating and condensing. The surface isn't really a surface at all. It's a statistical average, a large-scale description of restless microscopic chaos. This is the image that John Wheeler, one of the great physicists of the 20th century, had in mind when he coined the term quantum foam. He was trying to describe what space-time might look like at the Planck scale. Not smooth and serene, but turbulent and uncertain. A roiling, fluctuating substrate where geometry itself becomes probabilistic. It's a provocative image, and it's captured the imagination of physicists and science enthusiasts for decades. But it's important to understand what Wheeler meant and what he didn't mean. He wasn't suggesting that space-time is literally made of bubbles, or that it's fizzing like champagne. He was using metaphor to point towards something that resists literal description. At the Planck scale, if quantum mechanics applies to space-time itself, then geometry shouldn't have a single, definite form. Instead, it should fluctuate, existing in a superposition of many possible configurations. In quantum mechanics, this is normal. An electron doesn't have a definite position until you measure it. It exists in a cloud of probabilities. Could space-time be the same way? Could the distance between 2 points, the duration between 2 moments, the curvature of space, could all of these be uncertain, probabilistic, fluctuating? Wheeler thought so, and he called this hypothetical state quantum foam. Now, let's be clear about what this would mean. In everyday life, we experience space-time as stable. Distances don't fluctuate. Time doesn't stutter. Everything feels solid and reliable. But that's because we're looking at scales far, far larger than the Planck scale. Just as the ocean looks smooth from a distance, space-time looks smooth at accessible scales. The foam, if it exists, would only become apparent if you could somehow zoom into Planck scale resolutions. And even then, apparent might be the wrong word, because observation at that scale would itself be part of the quantum uncertainty. So what would quantum foam actually be? One possibility is that space-time at the Planck scale is a constantly shifting network of connections and geometries, tiny bubbles or regions where space-time curves sharply, appearing and disappearing in fractions of a Planck time, virtual black holes forming and evaporating before they can be observed, wormholes opening and closing, a frothing dynamic tapestry. But here's the thing, we don't know if any of this is true. Wheeler's quantum foam is not a confirmed description. It's a conceptual placeholder, a way of saying something strange happens here, without claiming to know exactly what. Different approaches to quantum gravity treat this regime differently. Some theories, like loop quantum gravity, predict that space-time is fundamentally discrete at the Planck scale, not foam-like, but more like a quantum network with well-defined, though probabilistic, structure. Other theories, like certain formulations of string theory, suggest that space-time remains smooth even at small scales, because the fundamental object's strings are extended rather than point-like. The foam never appears because the violent fluctuations that would create it are softened. By the string's extent, still other approaches suggest that spacetime itself isn't fundamental. It emerges from something more basic quantum information, perhaps, or entanglement patterns and below the Planck scale. Talking about spacetime at all might be meaningless. So, quantum foam is less a theory and more an idea, a way of imagining what happens when quantum uncertainty meets spacetime geometry. And it's useful precisely because it forces us to let go of classical intuition. It reminds us that smoothness, continuity, and stability, these things we take for granted, might be large-scale approximations, like the calm surface of the ocean hiding molecular chaos beneath. But we should hold this image lightly. Metaphors are helpful, but they can also mislead. The foam might suggest turbulence, randomness, chaos. In reality, quantum mechanics is highly structured. Probabilities follow precise mathematical rules. If spacetime fluctuates, those fluctuations would be governed by laws, just not the laws of classical geometry. The vacuum of space in quantum field theory is already known to be far from empty. Even in a perfect vacuum, quantum fields fluctuate. Particle-antiparticle pairs briefly pop into existence and annihilate. This is called zero-point energy, and it is real. Measurable effects, the Casimir effect, for example, where two uncharged metal plates placed very close together experience an attractive force, is a direct result of quantum vacuum fluctuations. So the idea that empty space is actually seething with quantum activity isn't new. What's new and uncertain is whether this activity extends to the geometry of spacetime itself. Does spacetime fluctuate the way quantum fields do? Does the distance between 2 points vary randomly on Planck scale timescales? Does the topology of space shift wormholes forming and vanishing, dimensions curling and uncurling? We don't know, and crucially, we may never be able to observe it directly. The Planck scale is so far removed from anything we can currently probe that these fluctuations, if they exist, would be completely invisible to us. They'd average out over any measurable distance, like trying to see individual water molecules from an airplane. So, quantum foam exists in a strange liminal space. It's not proven. It's not disproven. It's a possibility that helps physicists think about the deep structure of space-time without claiming certainty, and perhaps that's the right place for it to exist in the space between knowledge and mystery. Let's leave the foam behind now, at least for a moment, and turn to theories that make more concrete predictions. Theories that don't just gesture toward strangeness, but attempt to describe it precisely. Let's see what happens when physicists try to quantize spacetime directly, gently now, into the discrete geometry. What if we took spacetime seriously as a quantum object? Not just poetically, not just metaphorically, but mathematically. What if we applied the rules of quantum mechanics directly to the geometry of spacetime itself? This is the question that led to loop quantum gravity. It's one of the most ambitious and carefully constructed approaches to quantum spacetime, and it leads to a striking prediction: space is not infinitely divisible. At the smallest scales, it comes in discrete, quantized chunks. Let's understand how this works. In classical general relativity, spacetime is a smooth manifold, a continuous geometric structure. Curvature changes gradually from place to place. There's no smallest distance, no minimum area or volume. Loop quantum gravity starts with this framework but asks, what happens when we quantize it? In quantum mechanics, many physical quantities are quantized. Energy levels in atoms are discrete. Angular momentum comes in integer multiples of a fundamental unit. Electric charge is quantized. Could geometric quantities area, volume, length be quantized too? The answer, according to loop quantum gravity, is yes. But to get there, the theory had to make a radical move, abandoning the idea of space-time as a fixed background. This is crucial. In most quantum theories, you assume space and time exist as a stage on which quantum processes unfold. But in general relativity, space-time is dynamic. It's shaped by what's in it. Loop quantum gravity preserves this principle, called background independence. It doesn't assume a pre-existing space-time. Instead, space-time geometry itself is treated as a quantum variable, something to be determined. Not something given. To do this, The theory represents geometry using structures called spin networks. A spin network is a graphic collection of nodes connected by links, with quantum numbers attached to each node and link. These quantum numbers encode geometric information. Each link represents a quantum of area. Each node represents a quantum of volume. Together, they describe the quantum state of space itself. Now, this might sound abstract, so let's pause and think about what it means. In classical geometry, you can specify the area of a surface by giving a number, say, 10 square meters. That number can be anything. It varies smoothly. In loop quantum gravity, area is quantized. A surface can have an area of, say, 5 Planck areas or 6 or 7, but not 5.5. Area comes in discrete units, just like energy levels in an atom. The same is true for volume. Space itself is granular. This doesn't mean space is like a grid of tiny boxes. The structure is more subtle. The spin network isn't embedded in space, it is space, at the quantum level. At large scales, when you have billions upon billions of these quantum geometric elements linked together, the discrete structure averages out. You recover smooth, continuous geometry, just as a digital photograph made of discrete pixels looks smooth when you zoom out. This is how loop quantum gravity explains the success of classical spacetime. Smoothness is an emergent property at large scale, approximation of an underlying quantum. Geometry, one of the most appealing features of loop quantum gravity, is that it addresses singularities or ITIES. In classical general relativity, singularities like the center of a black hole or the Big Bang are points where density and curvature become infinite. The equations break down. In loop quantum gravity, this doesn't happen. Because volume is quantized, there's a minimum possible volume. Density cannot become infinite. Instead, when you try to compress matter further, quantum effects take over. In cosmology, this leads to an intriguing scenario. Instead of the universe beginning at a singularity, it might have bounced from a previous contracting phase. The Big Bang is replaced by a big bounce, a quantum transition from contraction to expansion. Similarly, inside a black hole, the singularity might be replaced by a region of extremely high but finite curvature, possibly leading to a quantum tunneling to a new region of spacetime. These are speculative ideas, derived from simplified models, but they demonstrate something important. Loop quantum gravity offers concrete, calculable alternatives to classical singularities. It also makes predictions about black holes. In particular, it suggests that the area of a black hole's event horizon is quantized. The horizon can only take on certain discrete area values. This is significant because black holes have entropy, measure of their information content, and that entropy is proportional to the area of the horizon. If area is quantized, so is entropy. Each quantum of area corresponds to a bit of information. This provides a microscopic explanation for black hole thermodynamics, one of the deepest puzzles in theoretical physics. So loop quantum gravity is not just philosophical. It makes specific, testable predictions, at least in principle. The challenge is that these predictions apply at the Planck scale, which is far beyond current experimental reach. There's also the question of how to recover general relativity completely. Loop quantum gravity describes the quantum geometry of space, but connecting this to the smooth, dynamic spacetime of general relativity, especially in situations involving matter and energy, is mathematically difficult. Progress has been made. The theory is internally consistent. It respects the principles of quantum mechanics and general relativity, but it's not yet complete. Another challenge is that loop quantum gravity focuses on gravity and spacetime. It doesn't automatically include the other forces of nature, electromagnetism, the strong and weak nuclear forces, or the particles described by the standard model of particle physics. Whether and how these can be incorporated remains an open question. Despite these challenges, loop quantum gravity stands as a remarkable achievement. It shows that it is possible to quantize spacetime while preserving background independence. It shows that discrete geometry can emerge from fundamental principles. And it offers a vision of spacetime that is neither perfectly smooth nor chaotically turbulent. but structured, quantized, and governed by precise mathematical laws for some physicists. This is the right path. Space-time is quantum, geometry is fundamental, and smoothness is what emerges when you step back. For others, a different approach is more compelling. One where space-time is not quantized directly, but softened by changing what exists within it. Let's explore that path now, gently, into the world of strings. What if the problem isn't space-time itself, but what we think exists within it? This is the starting point of string theory. Instead of quantizing space-time geometry, string theory proposes something more radical. The fundamental building blocks of nature are not point particles but tiny, vibrating strings. And this single change from points to strings has profound consequences for quantum space-time. Let's begin at the beginning. In standard particle physics, electrons, quarks, photons, all the fundamental particles are treated as point-like. They have no size. They exist at single locations in space. This works remarkably well. The standard model of particle physics, built on this assumption, is one of the most successful theories ever developed. It describes 3 of the 4 fundamental forces with extraordinary precision. But when you try to include gravity, the 4th force, using the same point-particle framework, problems arise. As we discussed earlier, the calculations produce infinities that can't be controlled. The core issue is that point particles interact at single points in space-time, and at those points, quantum fluctuations can become arbitrarily strong, leading to divergences. String theory offers an elegant solution. What if particles aren't points? What if they're tiny, one-dimensional loop strings vibrating in different patterns? Each vibrational pattern corresponds to a different particle. An electron is a string vibrating one way. A quark is a string vibrating another way. A photon is yet another pattern. The length of these strings is extraordinarily small, on the order of the Planck length. So at everyday scales, they look like points. But at very small scales, their extended nature matters. And here's the key. Because strings have length, their interactions are spread out. They don't occur at single points. This smooths out the violent quantum fluctuations that cause problems in point-particle theories. The infinities that plague quantum gravity, they don't appear in string theory, at least not in the same uncontrollable way. Even more remarkably, string theory predicts gravity automatically. When you work out the mathematics of vibrating strings, you find that one of the vibrational modes behaves exactly like a graviton, the hypothetical quantum particle that carries the gravitational force. Gravity isn't added to the theory. It emerges from it. This is extraordinary. String theory isn't just a theory of quantum gravity. It's a unified framework that includes gravity, quantum mechanics, and potentially all the other forces of nature. That unifying ambition is both string theory's greatest strength and its greatest challenge. But let's stay focused on spacetime. In string theory, space-time is not quantized in the way it is in loop quantum gravity. Geometry remains continuous, but the behavior of strings within that geometry prevents the catastrophic breakdowns that occur in point-particle theories. In this sense, string theory doesn't make space-time quantum by discretizing it. It makes quantum gravity work by changing what moves through spacetime. Now, string theory comes with a striking requirement: extra dimensions. For the mathematics to be consistent, space-time can't have just the 3 dimensions of space and 1 of time that we experience. It needs more. In the most common formulations, it requires 10 space-time dimensions, 9 of space, 1 of time. Other versions require even more. So where are these extra dimensions? The standard answer is that they're compactified, curled up into incredibly small shapes, much smaller than anything we can observe. Imagine a garden hose viewed from far away. It looks like a one-dimensional line, but up close, you'd see that it has another dimension, a circular dimension wrapping around the hose. Similarly, the extra dimensions in string theory might be curled up at every point in space, but at scales so small that we never notice them. The specific shape of these compactified dimensions has profound implications. It determines what particles exist, what their masses are, and how they interact. Different shapes yield different physics. This is both a feature and a problem. String theory doesn't uniquely predict the universe we observe. Instead, it allows an enormous number of possible configurations, perhaps 10 to the power of 500, or more, each corresponding to a different universe. With different laws, this vast landscape of solutions raises difficult questions. Why does our universe have the particular configuration it does? Is there a principle that selects it? Or are we simply one of many possible universes? These questions remain unresolved. But let's return to spacetime. One of the most profound insights from string theory is the idea of duality. This is the discovery that very different-looking descriptions can be mathematically equivalent. They describe the same physics in different languages. For example, there are dualities that relate a theory in a large space to a theory in a small space. What looks like a large extra dimension from one perspective looks like a small extra dimension from another, and both descriptions give the same observable predictions. This suggests something deep. Space-time geometry might not be as fundamental as we think. If different geometries can describe the same physics, then geometry itself might be emergent, a convenient but not fundamental concept. This idea is reinforced by one of string theory's most famous results, the holographic principle, formalized in something called the ADS-CFT correspondence. This is a duality that relates a theory of gravity in a higher dimensional spacetime, specifically a type called anti-de Sitter space, to a quantum field theory without gravity. Living on the boundary of that space, the boundary has one fewer dimension. It's like a hologram, a lower dimensional surface encoding higher dimensional information. This correspondence is mathematically precise. Calculations on one side match calculations on the other, and it suggests that spacetime itself, volume, distance, interior geometry might emerge from quantum entanglement patterns in a lower dimensional theory. In this view, spacetime isn't fundamental. It's a derived concept that appears when you have the right kind of quantum system. This is a radical departure from classical physics, where spacetime is the stage on which everything happens. Here, spacetime is part of the performance and not even the most fundamental part. Now, string theory has its critics. The main criticism is testability. The energy scales where string effects become important are far beyond what any particle accelerator can reach. The extra dimensions, if they exist, are too small to observe. The vast landscape of solutions makes specific predictions difficult. Some argue that without experimental verification, string theory is more mathematics than physics. Supporters counter that the theory makes indirect predictions about black hole entropy, about the unification of forces, and that it's internal. Consistency is a powerful form of validation. The debate continues. But what string theory undeniably provides is a consistent mathematical framework in which quantum mechanics and gravity coexist. It shows that smooth spacetime can remain continuous if the right ingredients are present, and it hints that spacetime itself might be emergent, arising from deeper quantum structures. For our question, when does spacetime become quantum? String theory offers a nuanced answer. Spacetime doesn't necessarily become quantum. Instead, the quantum nature of reality is always present, but it's encoded in the extended objects, strings, and their interactions. Spacetime remains a smooth arena, but its meaning is tied to the quantum states of strings. And at a deeper level, spacetime itself might not be fundamental at all. This is a different vision from loop quantum gravity. Not discrete geometry, but continuous geometry arising from quantum ingredients. Both are serious, mathematically sophisticated approaches. Neither is confirmed. And there's a third possibility, one that takes emergence even further. Let's go there now, softly, into the realm where spacetime is not fundamental at all. Here's a thought that might seem strange at first. What if space and time aren't real? Not that they don't exist, clearly we experience them. But what if they're not fundamental ingredients of reality? What if they're more like temperature or pressure, real, measurable, useful, but emergent from something deeper? This is the idea of emergent spacetime, and it's one of the most philosophically radical proposals in modern physics. Let's explore what this means. We've already seen examples of emergence. Temperature doesn't exist at the level of individual atoms. It's a statistical property that appears when you have many atoms interacting. Pressure rises from molecular collisions. Fluid flow emerges from particle motion. In each case, the emergent property is real. You can measure it. It obeys laws. It has causal power. But it's not fundamental. It's a description that applies at a certain scale, arising from microscopic dynamics that don't themselves involve that property. Could spacetime be the same way? At large scales, we experience smooth, continuous space and time. Objects are separated by distances. Events occur in sequence. Geometry has structure. But perhaps, at the most fundamental level, there is no space, no time, no geometry. Instead, there are more basic entities, quantum states, information, patterns of entanglement that, when viewed in the right way, give rise to the appearance of spacetime. This is not science fiction. It's a serious research program supported by concrete results in theoretical physics. One of the key insights comes from the holographic principle, which we touched on earlier. The holographic principle states that the information contained in a volume of space can be described by data on the boundary of that volume, like a hologram where a two-dimensional surface encodes a three-dimensional image. In physics, this was first realized in the study of black holes. Jacob Bekenstein and Stephen Hawking showed that a black hole has entropy, a measure of hidden information, and that entropy is proportional to the area of the event horizon, not the volume inside. This was puzzling. Why area and not volume? The holographic principle generalizes this for any region of space. The maximum information it can contain is determined by its surface area, not its volume. This suggests that the interior of space might be redundant. The real degrees of freedom live on the boundary. In the late 1990s, one Maldacena discovered a concrete realization of this idea, the ADS-CFT correspondence. This is a precise mathematical relationship between two very different theories. On one side, a theory of gravity in a higher dimensional spacetime and T-d space. On the other side, a quantum field theory without gravity, living on the boundary of that spacetime. These two theories are equivalent. They describe the same physics. Calculations on one side can be translated into calculations on the other. What's astonishing is this: in the boundary theory, there's no spacetime in the usual sense. There's a time dimension and some number of spatial dimensions, but not the interior bulk spacetime. Yet the bulk spacetime complete with curvature, black holes. Gravitational waves emerges from the quantum dynamics of the boundary theory, spacetime. In this picture is not fundamental. It's a useful way of organizing information about quantum states in the boundary theory. Distance in the bulk corresponds to certain patterns of entanglement on the boundary. Curvature corresponds to changes in those patterns. Black holes correspond to highly entangled states. This is a profound shift. Space is not a container in which things happen. Space is a description of how quantum states are related, and this idea has been extended. Beyond the specific case of ADS-CFT, physicists are exploring whether spacetime in our actual universe might also be emergent. One key ingredient is quantum entanglement. Entanglement is a phenomenon. Where do quantum systems become correlated in ways that can't be explained by classical physics? Measuring one system instantly affects the other, even if they're far apart. Einstein called this spooky action at a distance and was deeply uncomfortable with it. But experiments have confirmed it beyond doubt. Entanglement is real, and there's growing evidence that entanglement and spacetime geometry are deeply connected. In the ADS-CFT correspondence, the more entangled two regions of the boundary theory are, the more connected the corresponding regions in the bulk spacetime are. In the extreme case, entanglement can create spatial connections, something called an Einstein-Rosen bridge, or wormhole. This has led to a slogan, "Entanglement builds geometry." The idea is that what we perceive as spatial separation is actually a measure of how entangled quantum systems are. Close by means highly entangled. Far apart means weakly entangled. If this is right, then space itself is not fundamental. It's an emergent structure that arises from patterns of quantum information. Time might be emergent too. In quantum mechanics, Time is usually treated as an external parameter or background against which things evolve. But in quantum gravity, time might not be fundamental either. Some approaches suggest that time emerges from correlations between different parts of a quantum system. What we call the passage of time might be the unfolding of entanglement and information flow. This would explain why time has a direction, why we remember the past but not the future, why entropy increases, why causes precede effects. These might all be features of emergent time, not properties of a fundamental time parameter. Now, let's be clear, these ideas are speculative. They're supported by mathematical results in specific models, but they haven't been confirmed in the real universe. Still, they represent a coherent framework, and they offer a different answer to our central question. When does space-time become quantum? If space-time is emergent, it might never become quantum in the way particles do. Instead, quantum mechanics is always primary. Space-time appears as a derived concept when quantum systems are organized in certain ways specifically, when they're highly entangled and of certain information-theoretic properties at large scales. Where entanglement patterns are stable and well-defined, space-time is smooth and classical. At small scales or in extreme conditions, those patterns break down. Space-time becomes ill-defined not because it's fragmenting, but because the underlying quantum state doesn't have the structure needed to give rise to emergent geometry. This perspective also addresses the problem of quantum gravity in a different way. Instead of trying to force quantum mechanics and general relativity together, it suggests they operate at different levels. Quantum mechanics describes fundamental degrees of freedom. General relativity describes the emergent geometry that arises. When you have the right kind of quantum state, the incompatibility between them was never a contradiction, it was a category error. Like trying to reconcile the laws of fluid dynamics with the laws of molecular motion. They're both correct at different scales. This view has philosophical implications. If space-time is emergent, then reality at the deepest level doesn't look anything like our experience. There are no distances, no durations, no locations, just quantum information in some abstract configuration space. What we call the universe is a particular pattern in that configuration, and the smooth, continuous space-time we inhabit is like the surface of the ocean, a large-scale structure that emerges from restless quantum dynamics beneath. This can feel unsettling, but it's also liberating. It means physics is not failing when familiar concepts break down at the Planck scale. It's succeeding, revealing that those concepts were never meant to apply universally. Whether emergent space-time is the correct description remains an open question, but it demonstrates something important. There are coherent ways to think about quantum space-time that don't require quantizing geometry directly, and it reminds us that the deepest questions in physics often require us to question what we thought was most certain. Let's turn now to a more practical matter. What can experiments tell us about any of this? Gently, into the realm of observation, there's a humility built into modern physics, a recognition that not everything can be measured, not everything can be tested, not because we lack cleverness or technology, but because nature imposes fundamental limits. And nowhere is this more true than in the quest to understand quantum space-time. The Planck scale where quantum effects and gravitational effects meet is far beyond the reach of any conceivable experiment. Let's put this in perspective. The Large Hadron Collider, the most powerful particle accelerator ever built, can probe distances down to about 10 to the power of -19 meters. That's extraordinarily small, a billion times smaller than a meter. But the Planck length is 10 to the power of -35 meters. That's 16 orders of magnitude smaller than what the LHC can reach. Building a particle accelerator that could probe Planck-scale physics would require energies so vast that the accelerator itself would be larger than the solar system. And even if we could build such a machine, concentrating that much energy in a small region would create black holes, making the measurements impossible. So, direct observation of Planck-scale phenomena is not just technically difficult, it's physically impossible. Does this mean we can never test theories of quantum space-time? Not quite. It means tests must be indirect. One, of the most promising avenues is gravitational wave. Astronomy. Gravitational. Waves are ripples in spacetime produced by accelerating masses, especially violent cosmic events like black hole mergers and neutron star collisions. The LIGO and Virgo detectors have now observed dozens of these events. The signals match the predictions of general relativity with stunning precision. This is important because it tests gravity in extreme conditions, strong fields, high velocities, regions of intense spacetime curvature. If quantum gravity effects were significant at these scales, we'd expect to see deviations from classical predictions, subtle anomalies, unexpected damping or dispersion of the waves. So far, nothing. The waves behave exactly as general relativity predicts. This places tight constraints on any theory of quantum spacetime. Whatever happens at the Planck scale, it must not produce observable effects at the scales probed by LIGO. This is actually encouraging. It confirms that spacetime is classical over an enormous range of scales exactly. What effective field theory predicts? Cosmology offers another testing ground. The cosmic microwave background, the afterglow of the Big Bang, carries imprints of the very early universe. Tiny fluctuations in this radiation reveal how matter and energy were distributed when the universe was only a few 100,000 years old. Some theories of quantum spacetime predict subtle modifications to these patterns. For example, if spacetime is discrete at the Planck scale, that might leave an imprint on the statistics of cosmic fluctuations. Observations so far show no such imprint. The data align beautifully with models based on classical spacetime and quantum field theory for matter. Again, this constrains but doesn't eliminate theories of quantum gravity. Laboratory experiments provide a third approach. Physicists have conducted exquisitely precise tests using atomic clocks, interferometers, and quantum systems. For example, atomic clocks have confirmed gravitational time dilation at height differences of less than a meter. Quantum interference experiments have tested whether particles behave differently in gravitational fields. Tests of the equivalence principle, the idea that gravity affects all objects equally, have reached extraordinary precision. None of these experiments have detected deviations from classical spacetime or standard quantum mechanics. This tells us that if spacetime has a quantum structure, it's hidden extremely well. Any effects are smaller than current measurement precision, which is already astonishingly fine. There's also the possibility of indirect signatures in high-energy cosmic rays. If spacetime is discrete or has a granular structure, very high-energy photons traveling across cosmological distances might accumulate tiny delays. Different energies might travel at slightly different speeds, a violation of the usual principle that the speed of light is constant. Observations of gamma-ray bursts from distant galaxies have looked for this effect. They've found nothing. The photons arrive with no detectable energy-dependent delay. This places constraints on models with discrete spacetime, especially those where discreteness leads to departures from Lorentz symmetry, the principle underlying special relativity. So, what's the picture that emerges from all these observations? Spacetime behaves classically across every scale we've tested. From laboratory benchtops to gravitational wave detectors to cosmological horizons, the smooth, continuous description works. This doesn't prove spacetime is fundamentally smooth, but it shows that any quantum structure must be confined to scales far smaller than we can probe. Consistent with the Planck scale prediction, there's a philosophical point here. In science, not every question corresponds to an observable distinction. If the theories make identical predictions for all possible measurements, then the difference between them might not be physical, it might be a matter of interpretation or mathematical formulation. This happens in quantum mechanics. Different interpretations, Copenhagen, many worlds. Pilot wave make the same experimental predictions. Choosing between them is not an empirical question. It's a philosophical one. The same might be true for quantum spacetime. Different theories loop quantum gravity, string theory. Emergent spacetime might all reduce to the same observable predictions at accessible scales. If that's the case, experiments alone won't tell us which is correct. The choice might depend on other criteria, mathematical consistency, conceptual elegance, how well the theory integrates with other branches of physics. This is not a failure of science. It's a recognition that science has boundaries. Physics can tell us how nature behaves. It can reveal patterns, predict outcomes, unify disparate phenomena. But at the deepest levels, when we ask what is reality made of, or what is the fundamental nature of space and time, we might be pushing beyond what experiments can answer. That doesn't mean we stop asking. It means we proceed with humility. We build theories. We test what can be tested. We use consistency, elegance, and coherence as guides. We acknowledge uncertainty where it exists. And we accept that some questions might remain open, not forever, perhaps, but for a very long time. Living with that uncertainty is part of doing science at the frontier. Let's bring everything together now, softly, with care. We've journeyed far together, through smooth classical worlds and probabilistic quantum realms, through curved geometries and discrete networks, through strings and foam and emergence, and now it's time to ask, what have we learned? When does space-time become quantum? The honest answer is, it depends on what you mean. If you mean at what scale do our classical descriptions of space-time break down, the answer is clear, the Planck scale. Around 10 to the power of negative 35 meters, 10 to the power of negative 40 for seconds. At this scale, quantum uncertainty and gravitational effects are equally strong. The very concepts of distance and duration lose operational meaning. Trying to measure smaller scales would require energies that would distort space-time so severely. That measurement becomes impossible. So the Planck scale marks a boundary. Not a boundary in space, but a boundary of description. Below this scale, smooth continuous space-time is not the right language. But what replaces it? That's where theories diverge. In loop quantum gravity, space-time is fundamentally quantum. Geometry itself is quantized. Areas and volumes come in discrete units. Smooth space-time emerges when many quantum geometric elements are averaged together. In this view, space-time is always quantum. The question isn't when it becomes quantum, but when its quantum nature becomes visible. At large scales, quantum effects average out. At Planck scales, discreteness dominates. In string theory, space-time remains smooth, but the objects within its strings are fundamentally quantum. Their extended nature softens interactions that would otherwise produce infinities. Here, space-time doesn't become quantum in the same sense. Instead, quantum mechanics governs the strings, and smooth space-time is the arena in which they move. At a deeper level, though, string theory suggests space-time might not be fundamental. Dualities show that different space-time geometries can describe the same physics. Geometry might be derived, not primary. In emergent space-time approaches, space and time aren't fundamental at all. They rise from patterns of quantum entanglement and information. At the deepest level, there's no space-time, just quantum states. When those states are organized in certain ways, space-time emerges as a useful description. In this view, asking when does space-time become quantum is a bit like asking when does temperature become molecular. The question assumes categories that don't align with the underlying reality. So, which view is correct? We don't know. Each approach is internally consistent. Each is grounded in established physics. Each offers insights, but none has been confirmed by experiment. And perhaps none can be, given how far the Planck scale is from observational reach. What we can say with confidence is this: at every scale we've tested, from laboratory experiments to astronomical observations, space-time behaves as smooth and continuous. General relativity works beautifully. Quantum mechanics works beautifully. They just don't work together in extreme regimes. This tells us two things. First, smooth space-time is real and accurate where we live. It's not an illusion. It's the correct description at accessible scales. Second, that description has limits. It's not universal. At sufficiently small scales or extreme conditions, something different is needed. This is not a failure. It's how science works. Every theory has a domain of validity. Newtonian mechanics is accurate for everyday motion but fails at high speeds, where relativity takes over. Classical electromagnetism is accurate for large systems but fails at atomic scales, where quantum mechanics is needed. General relativity is accurate for gravity at accessible scales, but is expected to fail near singularities and at Planck scales, where quantum gravity is needed. Recognizing these boundaries doesn't diminish our knowledge. It refines it, and it points toward a deeper truth. Reality is layered. Different descriptions apply at different scales, and understanding how those layers connect, how microscopic quantum behavior gives rise to macroscopic classical behavior, is one of the great challenges of physics. So, when does space-time become quantum? At the scale where classical concepts stop being adequate. At the scale where quantum uncertainty and gravitational effects are both unavoidable. At the scale, the Planck scale, where measurement itself breaks down, and the notion of smooth geometry loses meaning. Not at a place, not at a time, but at a resolution, and what that means, whether space-time is discrete, emergent, or something else entirely, remains one of the deepest open questions in science. But knowing the question, understanding why it's hard, and appreciating the limits of current knowledge, that's wisdom. Let's rest in that wisdom now, gently, as we approach the end of our journey. There's a certain kind of peace that comes from knowing the boundaries of your knowledge. Not the peace of certainty, that's different, often brittle, but the peace of clarity, of understanding what you know, what you don't know, and what you might never know. This is where our exploration of quantum space-time has led. We've seen that space-time, at the scales we can access, is smooth and reliable. It bends, it curves, it carries waves, but it does so continuously, predictably. General relativity captures this with mathematical precision, and that description works. We've also seen that this smoothness cannot extend indefinitely. At the Planck scale, the assumptions underlying smooth spacetime, that distances can be measured arbitrarily precisely, that geometry has definite values, these assumptions break down. And we've explored several frameworks that attempt to describe what happens beyond that boundary. Each is brilliant. Each is incomplete. So we're left with uncertainty. And here's the thing, that's okay. Uncertainty in physics is not the same as ignorance. It's not giving up. It's recognizing that some questions exist at the edge of what can be known, at least for now, possibly forever. This kind of uncertainty requires a particular mindset. Not skepticism, which doubts everything. Not dogmatism, which doubts nothing. But epistemic humility, a clear-eyed acknowledgement of what evidence supports and what it doesn't. In the study of quantum space-time, epistemic humility means several things. It means appreciating that smooth space-time is a spectacularly successful description, not dismissing it as merely classical or just an approximation. Approximations can be true and useful. Temperature is an approximation, yet it governs real phenomena. It means recognizing that theories like loop quantum gravity, string theory, and emergent spacetime are serious intellectual achievements, not wild speculation. They're grounded in established physics, mathematically rigorous and conceptually coherent. But it also means acknowledging that none of these theories is confirmed. They're proposals, explorations, attempts to extend our understanding into a regime where current tools give out. And crucially, it means accepting that some aspects of quantum spacetime might be beyond experimental reach. Not temporarily, not we'll test it when technology improves, but fundamentally. If the Planck scale truly marks the limit of measurability, then certain questions about the microscopic structure of spacetime might never be answered by observation. This is not cause for despair. It's a feature of reality. The universe is not obligated to make itself fully transparent to human inquiry. There's no guarantee that every question has an empirically decidable answer. What we can do is explore as far as evidence and reason allow, build theories that are internally consistent, test what can be tested, and hold our conclusions lightly when evidence is absent. This attitude, this balance of curiosity and restraint is part of what makes science powerful. It's not arrogance pretending to know everything. It's humility willing to say we don't know yet, or even we might never know. There's also something philosophically profound here. If space-time is not fundamental, if it emerges from something deeper, then the reality we experience is, in a sense, not the deepest reality, the smooth, continuous world of distances and durations. the world where objects have locations and events have moments. This might be like the surface of a vast ocean. Real, yes, but resting on something more fundamental that doesn't resemble the surface at all. This is not new to physics. We've encountered emergence before. Solidity emerges from mostly empty atoms. Color emerges from wavelengths of light. Sound emerges from pressure waves. In each case, the emergent property is real. Touch a table, it's solid. See a sunset, it's orange. Hear a symphony, it's music. But the deeper explanation involves entities and processes that don't have the properties of the emergent phenomenon. If space-time is emergent, the pattern repeats at the most fundamental level. Space and time, the very stage on which reality unfolds, might be like solidity, color and sound. Real but not fundamental, arising from something that doesn't resemble space or time at all. Living with this possibility requires letting go of certain intuitions. We evolved to navigate a world of medium-sized objects moving at moderate speeds. Our intuitions about space, time, and causality are finely tuned to that regime. But there's no reason to expect those intuitions to apply universally. At very high speeds, relativity shows that time dilates and lengths contract, counterintuitive, but true. At very small scales, quantum mechanics shows that particles don't have definite properties, counterintuitive, but true. At the deepest level, space-time itself might behave in ways that defy intuition, not because nature is perverse, but because our intuitions were never designed for those regimes. Accepting this is liberating. It means we don't have to force reality into familiar categories. We can let it be strange. We can follow the mathematics and the evidence wherever they lead, even if the destination is conceptually unfamiliar. And we can find beauty in that strangeness. There's something aesthetically stunning about the idea that space and time, the most basic features of existence, might not be basic at all, that they might arise from quantum information, from entanglement, from structures we don't yet fully understand. It's a vision of reality as layered, deep, and more subtle than it appears, and it's a vision entirely consistent with what we've learned from physics over the past century. Reality is not what it seems. Solid matter is mostly empty space. Energy comes in discrete packets. Time flows at different rates depending on motion and gravity. Space can curve. Each of these discoveries required abandoning comfortable assumptions. Each revealed a deeper, stranger, more beautiful reality. The quantum nature of space-time, whatever form it takes, is likely the same. A deeper truth that challenges our preconceptions and rewards our willingness to follow the evidence. So, how do we live with the mystery? We continue exploring. We build theories. We test what can be tested. We refine our questions. We accept that some answers might take generations to find. Others might never come. And we find meaning not only in answers, but in the process of inquiry itself. There's joy in understanding how far we've come, in recognizing that questions about the fabric of reality are even askable, in knowing that mathematics can guide us into realms beyond direct experience. And there's peace in recognizing limits, not as failures, but as boundaries that define the shape of knowledge. Let's carry that peace now into the closing moments of our journey. So here we are, at the end of our journey through the quantum nature of space-time. We started with the familiar, the solid, predictable world of everyday experience, the smooth flow of space and time that shapes our lives. And we've traveled to the edge of knowledge, to scales so small that distance itself becomes uncertain, to regimes where the most fundamental features of reality might dissolve into something stranger and deeper. Along the way, we've encountered beautiful ideas: Newton's clockwork universe, Einstein's curved geometry, quantum superpositions, discrete geometric networks, vibrating strings, emergent space-time woven from entanglement. Each idea is a testament to human curiosity and ingenuity. Each represents decades of work by brilliant minds wrestling with nature's deepest puzzles. And yet, the question remains open. When does space-time become quantum? At the Planck scale, yes, that's clear. But how does it become quantum? Is geometry discrete? Is space-time emergent? Is it softened by extended objects? We don't yet know, and perhaps in some ways that's fitting. The universe is not obligated to reveal all its secrets at once. Science is a conversation with nature, and conversations take time. What we've learned tonight is not a final answer, but a map of the territory. We know where smooth spacetime works. We know where it's expected to fail. We know the scale at which quantum effects become unavoidable. And we know the outlines of several possible resolutions. That's progress. Real, meaningful progress. If you've stayed with me through this entire journey, thank you. Truly. These ideas aren't easy. They require patience, openness, and a willingness to sit with uncertainty. But they're worth contemplating, because they touch on the deepest questions we can ask. What is the universe made of? How does it work? What is real? And even without final answers, the process of asking, of exploring, of thinking carefully is valuable in itself. Before you drift off, let me leave you with one final thought. The smooth space-time you experience the distances between things. The passage of time, the stability of the world is real. It's not an illusion. It's not a mistake. It's an accurate description of reality at the scale where you live. And that's beautiful. The fact that there might be deeper layers, stranger structures, quantum foam or discrete networks or emergent geometry. That doesn't diminish the reality of your experience. If anything, it enriches it. It means the universe is more subtle, more complex, more wondrous than it appears. So, as you close your eyes and drift towards sleep, let yourself rest in that wonder. You live on the surface of an ocean whose depths are still being explored. And that's exactly where you're meant to be, if you found this journey meaningful. I'd be deeply grateful if you'd like this video, subscribe to Sleepy Science Tales, and share it with others who might appreciate these calm explorations of deep ideas. Your support allows us to continue making these journeys together. And there are so many more questions to explore, so many more mysteries to contemplate. But for now, rest. Let your breathing slow. Let your thoughts drift. Let the ideas we've explored tonight settle gently into the background of your mind. Spacetime is smooth where you are, reliable, continuous, and somewhere, far beyond measurement, far beyond imagination. At scales we can barely conceive, it might be something entirely different. Both truths can coexist. Both are part of the magnificent, layered, mysterious reality we inhabit. Thank you for joining me on Sleepy Science Tales. May your dreams be peaceful, your rest deep, and your curiosity never dimmed. Good night.